Okay, so let's just talk about interpreting confidence levels and interpreting confidence intervals. You will be asked a lot of questions, A, on the free response portion of the exam, and B, on the multiple choice portion of the exam. And the AP exam uses this wording almost exactly the same every single solitary time. And I'll just go through and tell you how theirs might be a little bit different. Okay, you want to be very, very careful. Please make sure you look at the directions. If it says interpret confidence interval, that's one thing versus interpreting the confidence level. And anytime you create a confidence interval every single solitary time, you're going to want to interpret the confidence interval. You only need to interpret the confidence level if the question asks you to do so. All right, so if we're going to interpret a confidence interval, that's basically saying like explain what you have produced, okay? So you will get very used to this. You'll be using it 1,000 times. So you hear me say it once, but you'll hear it a gazillion times in your homework and everything. Here's how you interpret the confidence interval. We are blank confident. So for example, we are 95% confident that the interval from 2.0 to 2.2 captures the actual value of the population parameter. Make sure you put it in context. So we're 95% confident that the interval from 2 to 2.0 captures the true mean amount of the population of students that go to the movies. Okay, how often they go in a month. So you're putting it in context. So we're basically like saying we've created a confidence interval with a number of standard deviations away from our point estimate, and we're saying that we're 95% confident or 80% or whatever that the interval we've created captures the mean. Now, the other way to interpret, the other interpretation we'll look at is the confidence interval. To say that we're 95% confident, what that means, that's basically interpreting the process. Okay, that's interpreting the process of basically how we created the confidence level. If we take many, many samples of the same size from this population, 95% of them will result in an interval that captures the actual parameter value. So basically, like I said, this is what the process is. The process is if we take many, 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 many samples and create many, 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 many confidence intervals, if we're talking about 95% confidence, 95% of the intervals will result in an interval that captures the true population mean, proportion, whatever. Okay, so let's just take a look at how we can interpret the confidence levels and intervals a little bit further. So the confidence level tells us how likely it is that the method we are using will produce an interval that captures the population parameter if we use it many times. So the level says if we have an 80% level, if we do many, many, many samples, 80% of the time we'll capture the true population mean or parameter. The confidence level does not tell us the chance that a particular confidence interval captures the population parameter. So it's not that there's an 80% chance that it falls within that parameter. That is completely incorrect because it's not a chance that it falls within that parameter. It's that if whenever we create this, if we did this 100 times, 80% of them would capture the population mean, proportion, or whatever. So please just be careful what that with that wording. Instead, what the confidence interval actually does is it gives us a set of possible values for the parameter, and within those 100, maybe 80 actually give us the true population mean. Okay, so it's not a chance that it falls in the interval. The chance that it falls in the interval, it either falls in the interval or it doesn't. That's either a 0 or 100% chance. Okay, this is talking about the method. The method that we create, 80% of them, if we had an 80% confidence level, would capture the true population in 80 out of 100 times. Okay, now we interpret confidence levels and confidence intervals in much the same way we're estimating a population mean or population proportion or some other parameter. All right, and later on we're going to be doing a lot of interpreting, so this is just sort of getting you used to it. Okay, so now we've talked about confidence intervals. How exactly are we going to construct them? So how do I go about taking that point estimate and creating a confidence interval? All right, number one, we're going to start with our sample data. We'll compute an interval that has a probability C of containing the true value of the parameter. All right, so we create an interval that has, we're 95% confident, 87% confident, whatever, that interval we create contains the true population mean or proportion. This is called the C confidence interval. So how do we construct a confidence interval? Since the sampling model of the sample mean x bar is approximately normal, we can use normal calculations to construct our confidence intervals. That's where 95% came from. 2 standard deviations above, 2 standard deviations below, but we can only do that if we know it's approximately normally distributed. So think about this. For a 95% confidence interval, we want the interval corresponding to the middle 95% of the normal curve. For a 90% confidence interval, we want the interval corresponding to the middle 90% of the curve. If we have an 85% confidence interval, we want basically it's the area of the curve where the population mean could possibly lie. So if we're using the standard normal curve, we want to find the interval using z-values. So let's say we want to find a 90% confidence interval for a standard normal curve. Now let's take a look at this. If the middle 90% lies within our interval, then the remaining 10% is outside the interval. Okay, so confidence intervals are always the middle of the curve. So we have the middle of the curve, here's your 90%. So that means that there's 5% outside of the confidence interval and 5% below outside the confidence interval. Now, what you're going to do is basically you're going to think about this. So if we want a 90% confidence interval, and this is sort of where our point estimate is, how many standard deviations do we have to add to get 90% above? And how many standard deviations do we have to add below to get 90, to capture the 90% middle portion of my curve? Now, the z-scores right here, you have these z-stars. All right, they're denoted with z-stars. They come from the standard normal curve centered about the mean 0. So when we were doing a 95% confidence interval, that was the z-score of 2 because we were 2 standard deviations above and 2 standard deviations below. So this z with a star is basically just telling us how many standard deviations am I above, how many standard deviations am I below to capture 90% of the middle portion of the curve. And it's important to be able to label this so that you can see this is called a critical z-score, that there's 5% below that z-score, 95% above, and for this one there's 5% above and 95% below. So sort of get used to drawing these curves with your confidence intervals. Now this z-star right here is called the upper critical P with probability P lying to its right under the standard normal curve. To find P, all right, so the probability P is just that 5% above. To find P, we find the complement of C and divide it by half. I don't necessarily do it this way. I just sort of think about it, but you can also do, if I have a 90% confidence interval, I can do 1 minus my confidence interval, which would be 1 minus 90, which is 10%. So I have 10% outside that confidence interval. If I take that 10% and divide it by 2, because I have an area above and an area below, that would give me my 5. So for a 95% confidence interval, we want the z-values with the upper P critical value of 2.5%. So think about a 95% confidence interval is in the middle 95% of the curve, and then we are going to have 2.5% above and 2.5% below. So this would be your critical z right here, the upper critical z and the lower critical z. For a 99% confidence interval, we want to use z-values with upper P critical value of 0.05. So that's saying you have 99% in the middle of your curve, you have 5% above and 5% below. So here's where your critical z-score would be here and here. All right. And then they always add up to 100%. Now, remember, and I talked about this on a previous slide, that the z-values tell us how many standard deviations we are above or below the mean. So to construct a 95% confidence interval, we want to find the values 1.6 standard deviations below the mean and 1.96 standard deviations above the mean. Well, where did that come from? So that came from right here. Okay, we want, if this is my 95% confidence interval, I'm taking up 95 of the middle portion of the curve. So basically I want to know, if this is my point estimate, how many standard deviations do I have to add above? How many standard deviations do I have to add below to get 95% of the curve? Well, when I do that, okay, I can find these critical z-scores just by what we did like in Unit 2. So think about this. Here's your critical z below here. If you do inverse norm of 0.025, remember your calculator always does the area to the left. It's the opposite. Okay, this is the inverse norm. It's the opposite of finding the area under the curve. It's giving the area under the curve to the left. left. So the area under the curve to the left is 0.025. Okay, and that gives us negative 1.96. So for the upper one, the area to the left of z is not 95, it's 97.5. So you're going to do inverse norm of 90.975. That gives you the positive 1.96. Notice these two will always be the same since it's symmetric. I highly suggest drawing the picture. It's going to help you decide how to find that critical z-score and what area is actually below each of your critical z-scores. All right, so why settle for a 95% confidence when estimating a parameter? The price that we pay for a greater confidence is a wider interval. So when we have a wider interval, it gives us a wider range of values where our true population mean or proportion would lie. So it's not as precise. I can't say exactly what it is. All right, so that's a wider interval. A smaller interval would give us sort of a more exact area of where the true population mean or proportion would lie. But with a smaller interval, we're not capturing the true population mean or proportion as much of the time. So when we calculated a 95% confidence interval for the mean of our sample of 100 teenagers with our unknown mean mu, we started with our estimate plus or minus our margin of error. Okay, now our estimate came from the sample statistic X bar. We took 100 seniors or teenagers and found out how many times they went to the movies. Since the sampling distribution of X bar is normal, central limit theorem greater than 30, about 95% of the values of X bar will lie within 2 standard deviations of the mystery mean mu. We don't know what that mean is yet. Therefore, our confidence interval can be written as 2.1 plus or minus 1.96 times 0.10, which is x plus or minus 1.96 times the standard deviation of x. Okay, so why the plus or minus? That's like saying the 2.1, I'm taking 95%. To get the 95%, I have to get half the percent above and half the percent below. All right, so this is gonna lead us to a more general formula for confidence intervals. So notice, how do we get the confidence interval? It's our statistic that we got from our sample, plus or minus, this is our critical value, so this is on our curve right here, sort of separates what's inside the confidence interval versus outside the confidence interval. That's your critical value, times the standard deviation of the statistic. Okay, so this is the general formula for finding your confidence interval. All right, now the confidence interval for estimating a population proportion has this form every single solitary time, no matter what we're looking at. All right, now the statistic is always your point estimate, but let's just take a minute and break these two down a little bit. Number one, the margin of error, this whole thing right here is the critical value times the standard deviation of the statistic. That whole thing is called your margin of error. Because think about this, you have your statistic, it's not going to be 100% correct, it's close, so we're giving ourselves some wiggle room above and some wiggle room below. Okay, we're taking up 95% of the curve and saying, hey, if we take up 95% of the curve, then most likely the population mean is going to fall, within my interval. So you, as the statistician, choose the confidence level, all right? So, and the margin of error follows from this choice. So do you want a big margin of error or a small margin of error? Because that critical value comes from your standard normal curve. That comes from your curve, and that is going to tell you whether or not you have a wide confidence interval or a more narrow confidence interval. So the critical value depends on the confidence level, 80%, 90%. Think about how much area of the curve you're taking up, 80%, 90%, okay? And the sampling distribution of the statistic. A greater confidence requires a larger critical value because you're taking up more area of the curve. The standard deviation of the statistic depends on the sample size n. Okay, all right, so general formula here is, here's your general confidence interval formula, statistic plus or minus your critical value times the standard deviation of the statistic. That whole thing is your margin of error. How much can we be wrong by, sort of. So what kind of error does the margin of error cover? It only covers random sampling errors due to chance variation. It doesn't cover things like undercoverage, non-response, or poor sampling design, taking poor simple random samples. This is error due to something larger than chance variation. Because this is basically, when I say chance variation, that just means that every confidence interval is going to be a little bit different because every statistic that you get from every sample is going to be a little bit different. Remember, the margin of error indicates how close our estimate is likely to be to the unknown population mean or proportion if we repeat the random sampling many times.